I'm Larry Pickett, and welcome back again, Dr. Masood. Dr. Masood was our speaker a few weeks ago, and he talked about regression analysis. And what we like to do in our organization, IATM, is we like to present speakers who come with topics from what I'll describe as soup to steak. And Dr. Masood has shared with us some steak about statistics. And so we're going to hear again from him. And again, Dr. Masood, thank you so much. I enjoyed your presentation. I'm looking forward to it today. And we'll turn it over to you.
Okay, thank you. Thank you, Dr. Larry. Okay. So should we start, Dr. Nipen?
Yes, sir. If you can share your screen.
Okay.
Yes, sir.
So I am sharing my screen. So the topic for the today, the scheduled topic for the today is the logistic regression. So as I always do, I will be sharing a situation or the case, right? Then we will be discussing the concepts accordingly, right? So this is the case. It is there. So hopefully the case you people must, right? So just go through this case, a very common situation. It is related to the graduate admission prediction, right? So just read, then we will be discussing. Okay? Just read.
Sir, if you can send me the case on WhatsApp or something, I can also share
Okay.
it on
Okay. Definitely.
on the chat.
Okay. I just missed that. Otherwise, I would have shared both the things well in time. Just a moment.
Or you can briefly tell the story.
Okay. Okay. Just let me share the case.
On chat? Okay.
Okay. Just a moment. I have shared both. Okay. Hello, Dr. Nepen?
Yes, sir. Thank you.
Okay. So this is the case. This is the situation that we are going to discuss today. So in this case is related to developing a model for the prediction of the graduate admissions in an institute of repute, right? So what is expected that we want to model a thing such that we can predict whether a student will be getting the admission or not, right? So there are certain features are being considered. The first one is the GRE score. The next one is the TOEFL score. The next one is the university rating. Means from where the person has did the UG, right? And after that, we have the strength of the statement of purpose on a scale of 5. Then was the strength of the letter of recommendation on a scale of 5. What is the CGPA that the particular applicant has obtained in the graduation examination? And one more variable, one more feature is there, means what the research experience that applicant is having. And we want to predict what will be the chance of the admission of that candidate, right? So this is the situation that we are going to discuss. So hopefully the case is clear to all of you, right? Okay. So now let us put them in some technical form. So here we are actually what we are going to do, we are predicting whether the student will be getting the admission or not. So this Y is whether the applicant is getting admission or not, right? And here we have certain features like x1, x2, x3. If we exactly say how many features, so let me just transfer it here. So there are GRE score, TOEFL score 2, university rating 3, SOP 4, LOR 5, and CGPA, and right, research experience is 7. So this is going up to X7, right? So on the basis of this, we want to know or we want to predict whether the candidate is getting the admission or not, right? Now, if we observe this feature, what we observe that this Y can take only two values, 0 and 1. 0 means no admission and 1 means yes admission. So we can put them in better terminology that will be common in all the situation, that 0 is denoting a failure and 1 is denoting a success. Is that okay? So we want to predict whether a student is getting the admission or not getting that. And here we have these features, right? So now here, as we observe that this Y is not numeric like the problems of the regression analysis, it is categorical in nature, right? Here we have categories, or we can say here Y is not measurable, Y is non-metric in nature, right? So in this situation, we will be going for the tools that they are known as classification technique. Means we want to classify Y on the basis of these features, right? And there are n number of classification features like decision tree. We can have naive Bayes. Um, we can have KNN, right? So there are n. We can also have support vector machine, and here we will be considering a particular type of classification technique that is known as logistic regression. Right. So here what we are going to do, we are going to predict the probability that Y is taking value 0 or Y is taking value 1 on the basis of these attributes that are being used so to predict about the admission. So this is the logistic situation that we are going to study. So hopefully the situation is clear to all of you, right? And right. So here we can't apply the regression analysis. Why we can't apply the regression analysis? Because here we don't have any Y feature which is numerical in nature. So here actually we are getting a Y that is being termed as a categorical in nature. So how it is being done? So in order to explain, I am taking a very small example that what we are going to do, then I will be coming back to this case. So suppose this is the example that I want to discuss. It is we want to predict whether a person will be a loan defaulter or on the basis of the loan amount. One more thing. So the technique that we are going to study in the language of analytics, it is the supervised learning. Just like the regression, it is a supervised learning. Why it is a supervised learning? Because we are having the label data, we want to predict about the Y, and we are considering the dependence relationship. And previously, in the previous session, we have studied supervised learning regression. Now we are going to study supervised learning classification. So in the language of analytics or the machine learning, these techniques are known as SLC. So we will be discussing this SLC. So as I have mentioned earlier also, we are having this situation that we want to predict whether the person will be a loan defaulter or not. Since we want to predict this loan defaulter, so this is our Y variable. And we want to predict this on the basis of the loan amount, that is X, right? So here I am introducing a term that is known as odds, right? Odds, we all know it is very much related with the probability. And what are the odds? Odds are the favorable outcomes divided by unfavorable outcomes. Suppose we want to know what are the odds of a person being a loan defaulter. What are the odds of a person being loan defaulter? So here we have 1, 2, 3, 6. So we have 10 observation. In the 10 observation or the 10 samples, if we count Y, so how many Ys are there? So there are 5 Ys. So favorable outcomes are 5 and unfavorable outcomes are also 5. So this is 5 upon 5, right? How it is related to the probability. So the probability of a loan defaulter is that will be the favorable outcome 5 upon total outcomes. So total outcomes are 10. So these odds are very much related to the probability. Now we are considering odds in two different situations. So what is the first situation? We want to consider odds of loan defaulter when person has taken high loan. Right? So instead of the entire sample set, we are considering only those people who have taken high loan. So how many persons have taken high loans? 1, 2, 3, 4, 5, 6. 6 people have taken high loan. And in the 6 people, in the 6 samples, how many yes are there? 1, 2, 3, 4. Right? So if we consider odds of defaulter, given person has taken high loan. So we have total 6 samples, and in the 6 sample, favorable means the loan defaulters are 4 and unfavorable, those who don't defaulted the loan are 2. So 4 divided by 2. So this is the first situation. Now if we consider the other situation, that is odds of loan defaulter when the person has taken low loan, right? So if we consider the people who have taken low loan, so this is 1, 2, 3, 4. So 4 samples have taken low loan. And in the 4 samples, there is only one Y. There is only one Y. This is Y. Otherwise, we have N and N, right? So here, what will be the odds of defaulter if the person has taken low loan? So it would be 1 by 3. And if we consider this odd ratio, so this odd ratio means odds of defaulter given high loan divided by odds of defaulter given a person has taken low loan. So it will be 4 by 2 divided by 1 by 3. So it will be 12 by 2, that is 6. Right. So what does this odds ratio indicate? It indicates that if a person has taken high loan, then there is 6 times the chances that he or she will be loan defaulter. Right? So this odds ratio gives us the message that there is a relation between the amount of the loan and whether the person is classified as a loan defaulter or not. So if the person has taken high loan, so there will be 6 times the odds of a person being defaulter as compared to low loan. So this is the odds ratio, that is the thing on the basis of which we make our model, right? So how the model are being formed here? So what will be the logistic model? Here we consider the odds ratio. So odds ratio means if the probability P is for the success, so for the failure, it would be 1 minus P. So this will be the P, right? And we will be connecting this with our model. So how the model is being proposed? So this is log of P upon 1 minus P, that is equals to beta 0 plus beta 1 x1 going up to beta 7 x7, right? So this model is known as logistic model. Why logistic? Because here we have used log. So that is a logic model. So this logistic is actually the log of odds, right? So this is the concept. So I'm showing you here. So what is why we use this to examine the existence of associative relationship between categorical dependent variable and several independent variable. What is the objective? Objective is to find the conditional probability of occurrence of event, that is known as class probability, given there are independent variable, right? So this is the binary logistic model that I have already explained. So this is the model that I have already explained. Okay. So this model we are going to apply. So conceptually, is there any question? Then we can discuss. Otherwise, we will be going for the case solving. So any question if that is there?
No, sir. Let's go to the case solving. Thank
Okay,
you.
just a moment, just a moment. Okay. So this is the case that we are going to solve, right? So I'm sharing my SPSS sheet. So this is the data set, right? So here the chance of admission, this is a dependent variable. And here we have these 7 predictors or the independent variable. Now, if we observe these 7 variables, GRE score, TOEFL score, university rating, strength of SOP, strength of LOR, and CGPA are the metric or the numeric data, right? They are the scale data. But the next variable, that is the research, that is an feature or the independent variable or the predictor, is a categorical one, right? So we want to use this. So just like the regression analysis, it also requires that all the predictors or the independent variables should be metric in nature. Now here the research is categorical in nature. Research is a nominal data. Means 0 means no research experience, 1 means the research experience. So we have to develop a dummy variable for the research feature, right? SPSS has the provision so to create the dummy variable for all the categorical variable. If we use some machine learning library, then we have to use one hot encoding or this type of encoding will be there. Anyway, since we are using this SPSS, so there are provision so to convert the categorical variable into the dependent variable, right? Now I'm going to run this. As we know, we all know that all the analytical tools, all the analysis, all the tools that are being used for analysis are available under the drop menu of analyze, right? Now this logistic regression is a type of regression. So we will be going to regression. Now in the regression, we have 2 logistic regression. One is the binary logistic regression, other is the multinomial logistic regression. So the present case is the category belonging to binary logistic regression, because here we have 2 categories only. The person is getting the admission or person is not getting the admission. So most of the classification techniques are actually being applied to this type of binary situation. Means we will be having 2 values. One is success and other is failure. Suppose if we have more than 2 categories, then we can think of the multinomial logistic. But trust me, most of the cases belongs to the binary. Whether the person is having CVD or the person is not having CVD, whether the person is a loan defaulter or person is a non-loan defaulter, whether the person is a healthy person or person is not a healthy person, right? So in most of the situation, we will be getting the binary logistic. So we will be selecting binary logistic. We click that. So here is so here we are getting this dialog box for the logistic regression. So the first entry is the dependent variable. So this chance of admission, which is a categorical variable, it is a dependent variable. And we will be selecting these 7 predictors or the independent variable, and we will be transferring them directly to the covariates, right? And this method is known as enter method because we will be taking all the independent variable, all the covariates in one go. There are other methods also, like they can be entered one by one or they can be removed one by one. Anyway, since we are going to run this analysis for the first time, so we will be taking the default method. That is, all the independent variable, all the predictors are being entered in one go, right? Now, this is the first button, that is the categorical button, right? If you click this categorical button, so here we will be having all the independent variables, all the predictors. These are the 7 predictors. So it is asking us to instruct the software, instruct the programming language that whether there is some categorical variable or not. So here we know that this research is a categorical variable. So we will be selecting this research and we will be transferring to this categorical column, right? So it will be creating the dummy variables. It will be creating the dummy variables, right? So we will be using this, right? Suppose in our case, there is no categorical variable, then there is no issue. Anyway, we have selected this and then we continue, right? Now we come back to another, to the main dialog box. So here we will be selecting the option button, right? Here we will be clicking Hosmer, Lomeshow, goodness of fit, right? We will be having this iteration history, right? These 2 things are required, right? We will be having correlation of estimate also, that in case we will be checking the multicolority or not. Then we continue. Now, just for the demonstration purpose, though it is not required, but just for the demonstration purpose, I am using the button save also, and it is giving us the probability. So we will be selecting the probability and we will be selecting the group membership also. Again, this is just for the demonstration that how this model is working. Now we will be pressing the OK button. So now this is the output, right? So is it okay? Any question up to this point? Is it okay?
Yes, sir. Yes, sir. Thank you.
Right. So now the first table, the case processing summary. So what does it indicates? It indicates that we have a total sample of 400. We don't have the missing observation, right? Because this case is being constructed for the demonstration purpose. So obviously it is not having any missing observation. But if we have large number of missing observation, then we will be going for missing value treatment. What are the dependent variable encoding? We have taken 0 as failure, that is not admitted. And here success is the person is getting and the admission. So this is 1, right? And here related to the categorical variable coding, there are 181 observations where the person is giving the values of research as no, and 219 who are showing that they have the research experience. And here remember, no is being coded as 1, right? The first category by default is being coded in the form of dummy variable as 1. And then we having 0, right? So this is the situation. Now we are going to discuss how this method actually works. So here we use a method that is known as likelihood, maximum likelihood estimation method. Remember in the last session when we used the regression analysis. So in the regression, we have used the ordinary least square or least square estimation. But here what we do, since the assumptions that are required for the least square estimation or ordinary least square estimation are not met, the assumption that we discussed in the previous session. So we can't apply the ordinary least square estimation. So what we do, we use the likelihood ratio estimation. So how they work? Let me explain this, how they work. So I am explaining. Here we have the likelihood, likelihood is actually the joint probability. Means it will be the probability of all the observations, means xi into theta. So this is the joint probability, right? So what we want to do, we want to estimate the coefficients like the beta that I have shown, betas, such that this likelihood will be maximum. Right? Why this is? Means we want to know that those values of beta for which the probability of getting these joint probability or the probability of getting these values will be maximum. Right? If we can able to find out the perfect relationship, then it will be exactly equals to the 1. But it is not possible. So we want to maximize the value of L. Right? So that's why this method is known as maximum likelihood estimation. Means we are estimating these coefficients or the logistic regression coefficients, so the likelihood of observing these values will be maximum. So this will be done. Now how it is being done? It is a recursive process. Recursive process means we start with null model. Means null model means where there is no independent variable, right? We start with the null model and then we introduce the features or the variables or independent variable, and such that we will be going for maximizing this likelihood, right? Since we start with the null model, so it will be having minimum likelihood, right? Now, since this likelihood involves some exponential coefficient, so it is not very easy to examine this likelihood. So instead of likelihood, what we consider? We consider log of likelihood, right? That is being denoted as LL, right? So if L is maximum, then LL will be minimum. Minimum means near to 0 and it will be negative. So again, in order to ignore the negative sign, so instead of LL, what we actually consider, we consider minus 2 LL. And it will become positive because the minus sign has been balanced. And we'll be looking for the minimum value of minus 2 LL, right? So lesser the value of minus 2 LL, better is the estimation. So this is the concept that we will be going to use here. So is it okay? Or any question? It is a bit mathematical. So if you people want, you can have, though these things are there in the PPT, but if you want directly, you can have the screenshot of this. So any question or should we move forward?
Let's move forward, sir. Thank you. We'll take
Okay.
all the questions later, at the end of the session.
Okay. No issue.
Thank you, sir.
Right. So now here, we will be discussing these things. Now, as you see here, this is the beginning model. Beginning model means we are starting with this solution. And as you see, this is a beginning model. And in this table, you see variables in the equation, there is no variable. And variable not in the equation, all the features, all the variables are here. So these are the variables not in the equation. So this is the null model. Null model means we are not considering any feature in this. And the null model minus 2 LL is 550.11. So you can write this value as, so for the null model, as you see here, just a moment, I am noting down the value just for the discussion purpose. Just a moment. right? So this I will be using later on. So for the null model, I'm just noting down, then I will be change the slide. I have from our table, the minus 2 LL null for the null model, minus 2 LL value is 550. Right? As you see, this is the value of 550.51111. So we have just noted down this value. Just a moment. Okay, right? Now we come to the our model, right? Means when all the features are being entered, right? And as you see, in the iteration history, it is a recursive process. So in the very first step, the values of minus 2LL that was 550 earlier has been reduced to 278. In the next step, it is further being reduced to 223, then 207. And finally, in the step 6 and 7, as you see, now the decrease has become negligible, right? So it is approximately becomes constant as 204.838, right? So this is means, so this is the initial value, and the estimation process or this recursive process is terminated at this level because now the decrease has become so negligible, right? So for the null model, the value was 550, and for the proposed model, means the model where we are having these values, this minus 2 LL value is being decreased to 204.838. Right? So this is the process that I have explained, that in order to have a good estimation, we increase the value of likelihood, right? So in the other word, we decrease the value of minus 2LL. So here we have decreased the value of minus 2LL from 550 to 204, right? Now we will be going to examine whether this decrease from 550, right? So let me note down just a moment. I'm using the annotation, right? Means for the null model, I'm writing down minus 2 LL values, minus 2 likelihood. For the null model, this value was 550.511. So this is right, that I have discussed. And for our proposed model or the full model, it has been decreased to 204.838, right? So this is the value. This is for our model 0.2043838. So now we want to check whether this decrease is significant or not. We want to check whether this decrease, so there is a decrease, there will always be decrease. We want to check whether this decrease is significant or not, right? And for this purpose, we use omnibus test of model coefficient. With the null hypothesis is that our proposed model is insignificant. Our proposed model is insignificant means this decrease in minus 2LL is negligible or insignificant. So what is the decrease? Decrease is from 550 to 204. So this is the decrease, right? And as you see here, we are having this p-value. So as per this table, we can say that this p-value is less than 0.001. So if we take the default value of 0.05, so it is less than, it means we reject H0. Reject H0 means the model is insignificant, is being rejected. So we can say that our proposed model is significant. Means these 7 features is able to significantly classify whether the person is getting admissions or not. So this is the first step. So hopefully this concept is okay with you, right? So this is the first step. This step is parallel to the regression analysis that is being done through the ANOVA table. Here we are using the omnibus test of model coefficient. Right? Now, after that, we are going to discuss the another concept that is related to Hosmer-Lomachenko goodness of fit, right? So this is the Hosmer-Lomachenko goodness of fit. Now this test is being used to examine, just a moment. So this test is going to examine whether our model is a good fit to the data or not, right? So here we will be going to examine goodness of fit of the model. So here we will be having the hypothesis. Our hypothesis is our proposed model, means proposed logistic regression model, is a good fit to the data, right? And how it is being done? For this purpose, for Hosmer-Lomachenko goodness of fit, we divide our sample into 10 parts, right? And here we compare the observed frequencies with the expected frequency. Expected frequency means if H0 is true, then what will be the value? So if our model is a good fit, then obviously the observed frequency, that are the real frequencies, are approximately equals to the expected frequency that is from the model. So if this is the case, then we will be getting low value of chi-square. And if the low value of the chi-square, we will be getting high value of p value, right? So as you see here we are getting low value of chi-square, and correspondingly the p value, here the p value is, that is significance is 0.989, which is a high value. And if we compare it with our default level of significance, that is 5%. So we are not rejecting, it means we are accepting the H0. Accepting the H0 means we are saying that our model, the proposed model, is a good fit. So this is the next step. Means we have examined that our model is significant. In the next case, we have examined that our model is a good fit for the data. So is it okay? Should we move forward?
Yes, sir.
Right. So these two things has been done, right? Now, the next question arises, what is the strength of the model, right? Because we want to examine our performance of the model. Here we require two things. Number one, on the basis of explanation, and the second one on the basis of prediction, or on the basis of the predictability. So we will be discussing strength or the level of accuracy of the model in twofold. First, we discuss through the model summary. So this is the model summary, right? Remember, this strength of the model in the regression is being done by R square value. Now, since the assumptions are not being fulfilled, so we can't calculate the R square values in the logistic regression model. So what we do, we use the proxy R square value. We will be calculating the proxy R square value for the logistic regression. Now here two proxy R-square values are very popular and they are being adopted by the SPSS, though there are a number of proxy R-square value. But here in the SPSS, they are being adopted. The first one is the Cox and Snell R-square, and the second one is the Nagelkar R-square. Now, this Cox and Snell R-square has a issue. And what is the issue? That Cox and Snell R-square can never reach. I will be showing you the formula if you are interested in the slide. Can never reach to 1. Right? Means as we know that value of R square lies in between 0 to 1, and for the perfect fitting, the R square value will be 1. But the formula for the Cox and Snell R square is such that it may never reach to 1. Right? So this value 0.579 does not give you the exact impression of the degree of the fitting or degree of the strength of the model. So it is always recommended that in this case, it is better to explain the Nagelkar R square. So accordingly, we will be discussing this Nagelkar R square. And this Nagelkar R square is 0.774. So we can say that around 78% is the degree of accuracy, right? So obviously this value is relatively high, reaching to 1. So we can say that our model is having a good strength. So we can say that our model is having a good strength, right? So this is the discussion related to the strength of the model on the basis of explanation. R square is being used for the purpose of explanation, means how the independent variable, how the predictor, how the features are able to explain the Y thing, right? So this is the discussion related to R square. Now we are going to discuss another related aspect, but now here we are not discussing about the explanation. We are actually discussing the actual performance of the model in the form of prediction purpose, right? So now we will be discussing the next one, that is the performance of the model on the basis of its prediction. So if our model is perfect, then 100% prediction would be correct. So for this purpose, we will be using this classification table. This classification table is also known as confusion matrix. So when we teach the analytics, or when we teach the scikit-learn or the packages that are being popular in the analytics, so here the term used is the confusion matrix. So both are synonymous. So as you see here on this side, we have the observed value. Observed values are the real values. So we are having 220 not admitted, and this is 180, they are being admitted, right? So not admitted are 200 plus 20. They are not admitted in the real data, and 180 are admitted in the real data. So these are the observed value. And here we are having the predicted value. So what do we mean by the predicted value? Predicted value means they are predicted through the model. Right? I will be showing you the data sheet also where these are values, right? So they are being predicted in the model. Now, if we consider this diagonal elements, so this diagonal element means 200 are the observed values, those who are not admitted, right? And 200 are the values, are the predicted value that those are not admitted. So they are the correct prediction. So if we write the correct prediction, so this is the value, that is 200, right? It is related to the negative value. And in the same way, the other element of the diagonal is 153, means 153 are those who are actually or observed as admitted, and they are also being predicted by the model as admitted. So this is the correct prediction. So 200 is the correct prediction for the negative values or the failure, and 153 is the correct prediction for the positive value or admitted. And if we consider the percentage of the correct prediction, right? So we will be getting 88.3. Means our model is able to correctly predict 88.3% of the samples, right? So this is known as hit ratio or percentage of correct prediction, right? And it is also known as accuracy. Means our model is having an accuracy of 88%. So this is a high value. So we can say that our model is performing well, right? Now, if we use some different language, that is when we use in the analytics. So I am putting them in another, just a moment. Right. So here this negative value is known as, this is negative. And this is admitted, so this is positive. Again, this is negative and this is positive, right? So this value is true negative. Why it is true negative? Because it has been predicted as negative and it is actually negative. And this value is known as true positive. Why true positive? It has been predicted as positive and it is actually positive. So this is true positive. And these two values, it has been predicted as failure or negative, but it is actually the positive value. So it is known as false negative. In the same way, it is known as false positive. I will be showing you this. And accordingly, we develop this concept, right? So hopefully up to this level, things are okay.
Yes, sir. Thank you.
So now this concept I am explaining on our PPT also. So just a moment. So here, these things here we have discussed, right? So this is the classification matrix that I was explaining, right? So here the things will be more clear because it is somewhat more apparent. So here we have two values. 0 means negative, like here that was not admitted. 1 means positive, that is they are being admitted. So these are the observed value. Observed values are the real values. And here we are having the predicted value. 0 is the negative and 1 is positive. Now here we are predicting, in this case, we are predicting as negative and it is actually negative. So this prediction is true and this is known as true negative. In the same way here, we are predicting as positive and we are predicting as positive this value and it is actually positive. So this is known as true positive. So these two are the correct values. So these two are the correct values, correct prediction. And the next two values here, we are predicting as negative. This value, we are predicting as negative, but actually it is positive. So this prediction is false and this is known as false negative. In the same way, so this is a incorrect classification. The same is here also. It has been predicted as positive, as you see, it has been predicted as positive, but actually it is negative. So this prediction is incorrect. And this prediction is known as false positive. So they are the false positive. And this hit ratio or the overall accuracy. So we expect that this accuracy should be high. But there is a concept that is known as accuracy paradox. Accuracy paradox means model with the higher overall accuracy also may not be a good model. Because, like I take an example here. Suppose here, suppose we want to predict whether the person is having cardiovascular disease or not, right? So here, what will be the success? Success is person is having cardiovascular disease, because here our concern is to find out whether the person is having any cardiovascular disease. And what is the failure? Right? Failure means no CVD. Right? Suppose in these two categories, percentage of correct prediction are, right? Suppose for the success, this is 50%, and for the failure, it has 100%. And they are approximately having similar type of samples, right? So overall correct prediction will be 75%. So we can say that 75% is apparently looks to be a good prediction. But actually what is happening here? Means here our main concern is to predict the person is having cardiovascular disease. So where this is our concern. And in this case, the correct prediction is only the 50%, right? So this model cannot be considered as a good model in spite of having 75% of the correct prediction. So this is for the labeled data set. Now, if we consider unlabeled data set, like suppose we are considering the case of fraud detection, and we have examined a number of financial transactions. As we know, in very few of the examples, we are getting the fraud detection, right? So suppose in our sample, what is the division? No fraud cases are suppose 99%, and fraud cases are 1% only, right? This is the typical data set, because getting fraud is a rare observation, right? And suppose we don't run any model. We don't run any model means we haven't done anything. We don't run any model. And we simply say that all transactions are no fraud transaction. All transactions are safe, no fraud transactions are there. Now, since this is heavily biased, this is heavily unbalanced, right? Sorry, this is we should write balanced. Just a moment. The first one is the balanced, and the second one is unbalanced, right? Since this is heavily biased toward unbalanced, right? And what we did, we haven't run any analysis, we haven't put any effort. We simply classify that all the transactions that are coming to be examined are being classified as no fraudulent. So we will be automatically getting 99% of the correct values, because this is highly unbalanced data, right? So this is not okay, because we haven't used any model. In spite of getting a high accuracy score, we can't say that our model is good. So because of this, we have a number of different features also, like sensitivity, specificity. We can use F1 score, we can use ROC values. So we have different features also, right? So it is just to give you the impression that accuracy score might be there. So these two things is being done, right? Now I am coming back to our output, and we will be discussing the next situation. Okay. So now we are going to discuss, means up to this, what we discuss, that our model is significant. We discussed that strength of the model is good. We have the percentage of correct prediction, means accuracy score of 88.3. But we will be interested to know that what are the features that are having, that are mainly responsible for the classification purpose, right? So we will be going to discuss the significance of predictors. So now we are going to discuss significance of features. Features means significance of the independent variable or the predictors. Means what are the features, what are the predictors that are playing role in this classification. Okay? In the regression, remember this is being done using the testing of the beta coefficient, right? We have taken beta equals to 0 if beta for H0, and if H0 is accepted, then that predictor become insignificant. And if H0 is rejected, then we say that that predictor is significant. Now, instead of this, instead of the beta, here what we do, we consider WALD. WALD is actually this B is the unstandardized coefficient divided by standard error of B, and then we square. Right? And this WALD follows chi-square distribution with 1 degree of freedom. So what we do here, we examine whether this WALD coefficient is 0 or not. And if WALD coefficient is 0 means that independent variable, that feature is insignificant. Right. So what we do, it is being done using chi-square, and we see if the p-value or the significance is less than 0.05, we will be rejecting H0. And rejecting H0 means that feature or predictor is significant, right? So it is being done. Now, if we observe how many features are having less than p values, this is the one. This is one, right? Next is the research. So from this table, we get the idea that there are two significant features that are mainly responsible for the classification in between person getting admission and person not getting admission are, one is the CGPA and other is the research. So as you see, CGPA B is positive. So it means it has the direct relation. Higher the CGPA, higher will be the probability of getting admission. And for the research, it is negative. Means, remember, in the research, we have 0 and 1. And the coding is being done for 0. Means, the negative value should be interpreted as positive because here the lower value is being taken. Means, lower the value of this, the person will be going towards 1. Means, higher means having the research, there are higher chances of person getting admission. Means we can recommend that actually the CGPA and the research are playing the vital role in order to classify whether the person is getting admission or not. Okay. So this is related to the variable discussion. So any question? So we have approximately done, just to show you how it is being done. Here I'm showing you this data sheet because we have put, remember what we did? When we go to analyze, then we go to the things related to the logistic regression. In the save, we have marked probability and the group probability, group membership, right? So how it is being done? We will be calculating the probability as I have explained, right? And here the classification cutoff is the default value, that is 0.5. So if the probability of 1 is greater than 0.5, we will be classifying that as 1, means success. And if the probability of the getting the value y as 1 is less than 0.05, we will be classifying that as 0. So now you can check. In the first case, the predicted probability is 0.99876, higher than 0.5. So it has been classified as 1. Here the probability in the third case, probability is 0.05, which is less than 0.05. So 0.05, so it is less than 0.5, so it has been classified as 0. So these are the situation, right? Now, if we see the first sample here, the predicted value is 1 and the actual value is also 1, right? But if we consider this case, means case number 7, here the actual value is 1 and the predicted value is 0. So this is known as misclassified cases. That forms the confusion matrix, right? So it is just to see means how this method works. So we have discussed all these concepts approximately. So now the floor is open for the question.